Okay, guys. So we're moving on to the next part of our module, which in this case is the strength of acids and bases. And hopefully you guys know that we have 7 strong acids. And if you didn't, that's okay. We're gonna list them right now, or I'm gonna list them. But right, so you have hydrochloric, hydrobromic, hydroiodic, you have nitric acid, you have perchloric acid, you have chloric acid, and finally sulfuric acid. Right, so these are your 7 strong acids, and then, so you have bases also, and the trick to learning bases, at least how I did it, and how your workbook tells you to do it, is that you kind of form a B starting from lithium down to cesium, then you turn to beryllium, up to strontium, and you just close it back up, and you kind of make a letter B out of it, and these are what are going to give you your strong bases. So it's essentially whatever's in this letter B plus the hydroxide yields a strong base. So yeah, it's just whatever's in that B plus OH gives you a strong base. And then back to module 10. So yeah, and then what does it mean for something to be strong? So if you have a strong acid slash base, it essentially just means that your substance has the ability to fully dissociate or fully break apart. That's a slash. Whatever is easier for you to remember, but it just essentially means that once you put like any of your strong acids or bases into water, they're going to fully dissociate into their said ions and they won't want to go back to each other. So if we take, for instance, HCl, which is hydrochloric acid, we put that in water and it becomes an H3O plus ion plus your Cl, well, chlorine ion. Oh my god, why did I say chlorine? But okay, anyway. So yeah, and then as we can see here, we have an arrow pointing in one direction as opposed to the double arrows that we had been doing because of equilibrium. And that's just because, like I said, since they fully dissociate, there's not even a little bit of it left that's HCl in the product, so it won't turn back into HCl. It just fully goes into its ions, and that's the case for all your strong acids and all your strong bases. So then because of that full dissociation, it makes it really easy to find the pH. Let me make this thinner. Yeah, so to find the pH of strong acids or bases, okay, yeah, I don't know, I had a second where I thought I was misspelling bases, but okay. So this is basically to find them, I'm going to take the HCl example just because it's already there. Yields H3O plus Cl minus. And just what this does essentially is that since it fully dissociates, whatever you start off with is what you end up with. So if, say, initially I had 1 molar of HCl, water doesn't matter, and we have 0 of our products because we haven't made it yet, right? So then our change is going to be the 1 molar, because since it fully dissociates, whatever you start off with is what you end up with. And in this case, we're subtracting 1 molar, and in this case, we're adding 1 molar. So that at equilibrium slash our final, which I would say final, but then that would be ICF instead of ice table. But yeah, oof, yeah, that's right. I forgot to put my dash here that it doesn't matter. So then here we have 0, here we have 1 molar, and here we have 1 molar. So if we're finding the pH, and the formula for pH is the negative log of H plus, and we have our H plus concentration right here, right? Because it's H3O can be replaced with H plus, it's the same thing. So we do log of 1, which log of 1 gives you 0. So this is a very strong acid, because if your pH is 0, that's ouch, don't let it touch your skin, right? So it's pretty easy with strong acids and bases, just because whatever you start off with is what you end up with, but you need to keep track of if it's balanced essentially. Because let's take for instance barium hydroxide, and I'm going to give 0.04 molar of barium hydroxide. But, going back to the periodic table, barium has a charge of 2 plus, right? Because it's in our second row, and that's a +2 charge. And that's where barium is. So because barium has a charge of +2 and OH has a charge of -1, this is barium hydroxide, but our OH turns into 2, right? So if we're gonna fully dissociate this, which, okay, so just saying, you might see me not write down the water in cases of the strong acids, just because strong acids strong acids and bases fully dissociate. So like the water is there to tell you that that's what you're dissolving it into, that's what they dissociate into, but it's not necessary to write it down as long as you know what's happening. Right, but now looking at it, it's not balanced, so we need to put a 2 in front of here. So we're working it how we did our other ice tables. Initially we have 0.04 molar and none of our products. Our change is going to be that 0.04 molar, adding it on this side because we're creating products. Except here, since we have this 2 in front of it, it's going to be plus 2 times the 0.04. So that our final products are 0, 0.04, and 0.08 molar. Right, so then we're still trying to find our POH. So then to do that, well, we're trying to find our pH. We need to find our POH first because that's what's given to us, this OH concentration. So POH is equal to the negative log of our OH ion, right? So then we just do negative log of 0.08, and we end up with your POH being 1.1. Yes. So then to find pH, we simply do 14 minus 1.1, which gives us 12.9. And that makes sense when you're considering that this is a very strong base, so our pH should be fairly high, right? So then we can do another practice problem. So I'll take away the HCl. Oh my god, that little line is going to annoy me. Cool. So then what if we just do, okay, so I'm going to give you guys 0.03 molar of chloric acid, which is HClO3. So then we set up our formula, and that breaks apart into H plus ClO3 minus. Initially we have 0.03 molar, 0 and 0. Our change is 0.03 molar. So that final we have 0. and 0.03. Oof, you guys just saw that my battery's running low. But that's cool. We'll finish this problem and then I'll plug in my computer. So then we do our pH is equal to the negative log of our H concentration, which is 0.03. So our pH should be 1.52, which again makes sense because it's a strong acid. So you should have a fairly low pH for a strong acid. So then one final example would be 0.02 of sodium hydroxide. And then NaOH breaks apart into Na plus and OH minus. So this is 0.0200 minus 0.02 plus 0.02. So you end up with 0, 0.02, 0.02. So first step, POH, negative log of 0.02 gives us 0.7, which is just, it's rounded. Because I think you get like 0.69 something, so I'm rounding it to 0.7. So then pH is equal to 14 minus 0.7, which is 13.3, and that's a high pH for a strong base. So then that's essentially it for strong acids and bases pH. So all you have to remember is that when it comes to a strong base, you find the POH first, and then you find the pH by just 14 minus POH. But with a strong acid, you can just find the pH directly from your H plus concentration.